And I guess I thought my built-in audience is probably interested in analysis because you all watch these analysis videos, right? So anyway, I thought what I'd do is basically follow up in Ruden's book, and I talk about Jensen's inequality. All right. This is a pretty cool result. So let me just state it. Okay. So it let mu be a positive measure on a sigma algebra um, mu in a set omega so that a little too close there. Eh, Okay, so that the measure of omega is one. So incidentally, this is normally known as a probability space. Okay. So that is actually an entryway into probability theory via measure theory. You look at measure spaces where the measure of this whole space is one, right? The sort of fundamental value in probability theory, right? So we're really working in a probability space, but for the purposes of what Rudin is doing, he doesn't really care about the probability implications. So we're just taking a set of measure one. Okay, it really doesn't matter. It can be any set of measure one. This could be the unit interval, actually the interval I talked about last time. The interval from 0 to 1, right? I did that at the end of the video. Like that's a valid space for this problem. Um, so uh, yeah, so um, f is um, if f is a real function and the integral over omega of f d mu is finite. I guess I'll put absolute values in case it's not positive. Um, uh, A is less than F is less than B. Um, and phi is convex on the interval from A to B. Um, actually, incidentally, I don't really need to assume that I don't really need to assume that I don't really need to assume that f's integral is finite. I just need to assume that it's measurable because I have this boundedness condition, and the space that we're integrating over has measure one. So as long as I can integrate f, it's guaranteed to have a finite value. So anyway, just saying that for the record. Yeah, so phi is convex on AB. Then, and here's the big statement, phi of the integral from or the integral of f is less than or equal to the integral of phi composed with f d mu. Okay, so that's Jensen's inequality. Okay. Now, if you watched my Reese representation theorem series, then you know what a positive measure is, you know what a sigma algebra is, you know what it means to integrate a function. I think the only thing here that I didn't really talk about is convex. Um, I think convex is a relatively straightforward concept. Um, but let me talk about that a little bit. Okay. So let's go to a new page here. So the definition of convex. So let um uh phi from A B to R be a function satisfying um satisfying phi of 1 minus lambda x plus lambda y less than or equal to 1 minus lambda phi x plus lambda phi y for x and I don't know why I put a comma there. Let's do that again. For x and y in a b and um, lambda between 0 and 1. Okay? So that's the definition of convex. Um, this is equivalent to um, uh, phi t minus phi s over t minus s. So something like a difference quotient, right? A slope of the secant, right, is less than or equal to phi of u. That's a phi there. Minus phi of t over u minus t for a less than s less than t less than u less than b. Okay, so this is the form we're going to use. Okay, let me just indicate why these are equivalent. Okay, so uh, let lambda equal um, x minus t, or no, 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 wait, I want to get this right. Hold on, hold on. Let's try again. Let's try again. Let lambda equal, yeah, yeah, u minus t over um, u minus s. Okay. Okay. So I think if you look at this interval here, these inequalities, you can tell that uh you know the length of the interval from t to u, that's what u minus t um is smaller than the length of the interval from u to s. So this number is certainly less than 1, right? But it's also clearly positive. Okay, so this is in the closed interval from 0 to 1 for sure. I mean, it's not equal to 0, okay? But that's basically how you prove this. So your u becomes your x and your s becomes your y, and then t stays t, okay? And then we just apply this inequality with this value of lambda. And if you undo the algebra there, you should find that you get what you need. So basically the expression in here becomes t. Okay. And from there you're ready to you're ready to go. So I don't need to say any more about that. I think that's pretty straightforward, but this is the form that Rudin is going to use in his extremely slick proof. Okay. This proof is like this proof is hilariously short compared to the Reese representation theorem that took like 15 videos for me to get through. Um, all right, get out of my way. Okay, there we go. So let's do the proof. Jensen's inequality. Okay. So first let t equal this is so funny to me. The integral of f. Okay. So that's my t. Okay, recall that um the measure of omega is 1 and f is sitting between a and b. So that means that t is sitting between a and b. Okay? Okay. So uh so we don't have to worry about that. Okay. Um there's a slight concern here. Uh there's a slight concern of like f equaling one of the endpoints or t equaling one of the endpoints. But if that's really the case, then we can actually argue that f is equal to that constant value almost everywhere. And then from there, we can treat f like a constant function, and then Jensen's inequality is no big deal. So, I'm safe to assume that it's strictly between a and b. Okay. Um, so, but I mean, the inequality holds for all x, so it really shouldn't be equal to the endpoints. But I'm just saying, in case you're worried about doing a limit here, it's not a problem. Um, I don't want to sit here and argue about the endpoints, so I'm just mentioning, even if it did equal the endpoints, it wouldn't matter. Okay. So now, uh, uh, um, oh yeah, well, I guess the simple point is that f minus a is a strictly positive function, so its integral has to be strictly positive, right? So, and then b minus f is also a strictly positive function, so its integral has to be strictly positive as well. Okay, sorry, that's the argument I want to say. All right. Um, so now let beta equal the supremum of those quotients from the previous page. So the quotients that I mean here are the ones on the left side. So these. Now remember, t is fixed, okay? So we're going to take the supremum over s of um, uh, phi of t minus phi of s um, over t minus s. So s here is between t and a. And don't forget throughout this proof that that t here is fixed, right? We have specified t. So t is not a variable here. T is sitting still. Okay, but here s is moving. And I'm taking the supremum of all of these difference quotients over this interval here. Okay? All right. So that's the first step. And then um uh then for sure this is less than or equal to the right-hand side of the previous page. So this, okay. So let me write that down. Less than or equal to phi of u minus phi of t over u minus t for u between t and b. Okay. So I have that inequality. Okay. Um, and then we clearly have um, beta greater than or equal to phi of t minus phi of s over t minus s for a less than s less than t. Okay, because b was the supremum of all of these, so it has to be greater than or equal to that. But it's less than or equal to this because every one of these is less than or equal to every one of these. So if I take a supremum, it has to still be less than every one of these. Okay? So now we have these two inequalities. Okay. Um, and so now we're going to now we're going to conclude then. So therefore, beta times u minus t is less than or equal to phi of u minus phi of t. Okay. Um, uh, for t less than u less than b. Okay, so I'm just multiplying by u minus t. And the other one is beta of t minus s is greater than or equal to phi of t minus phi of s for a less than s less than t. Okay? And now we're just gonna combine these into a single statement. Okay? So I want like a uniform statement because you can see there's an obvious symmetry here. Okay. But if I want to combine these, then what I need to do is flip one of these around. So let me figure out which one I'm trying to flip around here. Uh, I guess, I guess, yeah. Uh, hold on. Hold on. Okay. Yeah, which one am I trying to flip around? I'm not sure which one I want to flip around. Maybe it doesn't matter which one I flip around. Maybe that's the ultimate truth here. Uh, yeah. Yeah. Okay. Well, let's just flip this one around, the bottom one. So if we flip it around, it says that beta times s minus t is less than or equal to phi of s minus phi of t. Okay, and that holds for these values. Okay, so now if you compare these two, so let me highlight what I'm talking about here. So if you compare this one with this one, you see that essentially they say the same thing. Okay. Um, but here the U value is allowed to be in this region. Here the S value is allowed to be in this region. If I actually have T here, then they're equal, right? The left-hand side is 0 and the right-hand side is 0. So if I actually take T, then they're equal. So putting these together means that if I have any value in the entire interval, then I know for sure that I have this inequality. So I can replace U or S, whichever way you want to think about it, by anything in the entire interval. So let me write that down. So for A less than S less than B, we have um, beta times S minus T is less than or equal to phi of S minus phi of T. Okay. So that's the inequality that I have um, for all t. Okay. For all s, sorry, for all s in the interval. Okay. And um, now what I'm going to do is note that I didn't prove this, by the way. But if you stare at this definition for a while, I think you can convince yourself that that this function has to be continuous. Okay. So like if you pick a point, um, if you pick a point like uh, um, like S, where you want it to be continuous, then then all you have to do is multiply both sides by t minus s, okay, and then let s approach t, and then clearly this numerator would have to approach t because, or the numerator would have to approach zero because, the right-hand side is like a fixed value. But then if I let s approach t, then, the right-hand side will go to zero, okay? So that's one way you can do that. Um, uh, we have to think about absolute values here a little bit, to make this proof actually work for the record. Okay, but my point is uh, that a convex function has to be um, continuous. Okay. Um, uh, Actually, root improves this. Okay. Um, uh, I think root improves this with like bounding this on either side. I guess that's the way you can go, right? We could add another point in here. Yeah, Rudin takes 4 points. So yeah, let me go to the next page and I'll quote Rudin's proof. It's a pretty straightforward one. So I'm gonna skip it. Um by let's see. Theorem 3.2 in Rudin. Real and complex analysis, right? Papa Rudin. Okay. You can read it. It's really not a hard, it's really not a hard proof. Um, he kind of describes it geometrically, but you can write down formulas using the inequalities that we have here. Okay, just put another point in, get another quotient going over here, and then multiply by t minus s, like I said. Because what I did will actually technically only tell you that, the limit here will be less than or equal to zero. So we need a bound on the other side to make sure that we don't have negative number problems. Okay. If we knew other stuff, about phi, we could make the proof a little simpler, uh but um but yeah, basically this is the proof. We're trapping it between lines of a certain slope, right? And that's basically what you're doing when you multiply by this, right? And then let t approach s, right? You're doing you know, you're doing a linear thing, right? Uh, you know, because it's trapped between these lines, it's forced to be continuous. Um, so, uh, okay. Yeah, like I said, I'm not gonna go through that whole proof, but phi is continuous. O U O U S. There we go. So phi composed with F is measurable. Okay. So we already had F measurable. I guess I guess I should have said that more explicitly, measurable. Um, I'll put that in parentheses because it's not strictly required. If we have measurable in this, we automatically have that. So I just wanted to say it, I guess. But yeah, we have a measurable function here. That's not quite the way Rudin phrased it. I didn't want to introduce L1 here. It just feels excessive. Okay, so anyway, that function's measurable. Okay. And so now what we do, we let S equal f of x. Okay. So that means we get beta of f of x minus t is less than or equal to phi of f of x minus phi of t. Okay. And now apply the integral. Okay. So, in case you're worried, I mean, this is a measurable function. Okay, it's greater than or equal to this. And I can apply the integral. If this integral happens to be infinite, then whatever, it's fine, right? The inequality still holds. So I don't really have to worry about applying the integral here. And all I did here is subtract a constant. So let's apply the integral here over omega of f of x minus t, um, which is less than or equal to the integral for omega, sorry, d mu, I forgot d mu, of f of x d mu minus this. Okay, now we have to remember that x is the variable here, okay? So x is the variable. So everything else is fixed. I mean, in particular, T is fixed and beta is fixed. Okay. So those values are staying the same here. So this is actually integrating a constant function over a set of measure one. Okay. So remember that we have linearity. Okay. So this is just phi of t. Okay. All right. Since the measure of omega is equal to 1. Okay? Right? Normally it would be this times the measure, but the measure is 1. Okay? And then let's look over here at the right-hand side. I think I need a little more space to explain this, but if we look at the right-hand side there, we have the integral of beta f of x minus t d mu over omega. This is equal to beta times the integral over omega of f d mu minus um, beta of the integral over omega of t d mu. Remember, t is fixed here, and this is a set of measure one. So if we also recall that this was the definition of t, so don't forget that was the definition of t at the beginning. So this is actually beta t minus beta t. So this is 0. Okay? Okay, so that's 0 here. 0. Okay? And now, if we remember that, again, if we remember that t is, if we remember that t is the integral of f, okay, then this is phi of the integral, and this is the integral of phi of f, and the difference is greater than or equal to 0. So therefore, that implies that 0 is less than or equal to the integral over omega of phi composed with f d mu minus the integral omega of uh phi of the integral f d mu. There we go. So that means that phi of the integral over omega of f d mu is less than or equal to the integral over omega phi composed with the f d mu. And that's the end of the proof. All right, cool. So yeah, that was way easier, right? That was way easier. So what I want to close with then is a cool application. So here's a fun application. Um, so phi of x equals e to the x is convex. Okay. So if you look at the difference quotient, um, if you look at the difference quotient condition, okay, that we talked about, this one, then if you consider the mean value theorem, you see that it's sufficient. Um, it's sufficient to say that um, it's sufficient to say uh, that the derivative is increasing or non-decreasing, if you want to be technical about it. Okay, so this basically implies that since phi prime, which is equal to e to the x as well, is increasing, you can prove that it satisfies this inequality using the mean value theorem, right? Because like this will be a derivative in here, and this will be a derivative in here, and the value in here is less than or equal to value in here. So boom, right? That's all you really need. Okay, so that is convex. Okay, and so we let omega be a finite set, so it'll just be 1 through n. Okay, and then we'll set the measure of I to equal 1 over n. Okay, so this is a finite measure space. If you think about it, then that means that the measure of omega is n over n, which is equal to 1. Okay, this is a very classic sort of probability space here, right? So then um, if we let um, f of I equal xi. So uh, these are real numbers. Okay. So this is my measurable function. Okay. Then by Jensen. So you actually you have to think about this a little bit, but it's kind of clear because in this context, every function is a simple function. So you can easily calculate that the integral of a function here is the sum of the values times the measure of each input value, right? Right, you can split it up into the disjoint pieces, and then it has a single value on that, and the measure is 1 over n. So we simply get xi to the 1 over n. So then we have the integral. So this is phi of the integral mega f d mu is less than or equal to the integral over phi of phi composed with f d mu. Okay, unraveling what this all means in this context, this is just the average of these values. Okay, so this would be e to the power um, 1 over n times x1 plus x2 all the way out to xn. And that's less than or equal to 1 over n times the sum of e to the xi's xn. Okay, so we get this inequality, which is pretty cool. But um, now if y1 through yn are positive numbers, then yi is equal to e to the xi, okay? And going to the next page here, and uh, y1 times y2 times all the way out to yn would then be equal to e to the x1 times e to the x2 all the way out to e to the xn. So that's equal to e to the x1 plus all the way out to xn. Okay. So then we can apply the 1 over n power to this. And then we can apply the exponential rule. Um, okay. That says this is e to the 1 over n times x1 plus out to xn. Okay. And we already had that. So that's less than or equal to 1 over n times the sum of the e's. Okay. And that's now the same as the sum of the y's. Y1 plus y2 all the way out to yn. So this is the arithmetic, geometric, the AMGM mean, arithmetic geometric mean inequality. Okay. So this is actually like a pretty cool proof of that. Um, Rudin shows some other examples, but this is like a really powerful idea that's just um, contained in this relatively simple result, right? And I think that's extremely cool. So, so I think I'll go ahead and end it there. I know this wasn't as long as my previous videos, but I hope that's okay. So I will, I'll check in with you later. In the meantime, rate, review, and subscribe. Let me know if there's something you want me to talk about. Check out those AI training links if you're interested in that. I mean, if you hate AI stuff and you're just like morally opposed to it, then don't do that. I understand. We all make compromises in life, or we don't. We do or we don't. No, I'm just saying, like, I've made my peace with it, but you don't have to. I'm not here to tell you what's right or what's wrong. So anyway, I'll see you on the next one. All right, keep being against the algorithm. Is that my catchphrase? Anyway, bye everybody.